In this video, we're going to look at angular and linear velocity. We're going to look at how to convert between those two ways of measuring speed. And we're going to look at the different types of angular velocity that we can have that are going to commonly show up for us. So angular velocity is just a measure of how fast something is spinning. So for example, if I have a large sprocket on a bike, and we're pedaling that bike so that the sprocket is revolving, angular velocity or angular speed, which might be a better way to say it, angular speed is just going to be a measure of how fast you're spinning it when you pedal. So we could measure that using revolutions. We could measure how fast it's spinning using degrees, because degrees measure circular motion. We could measure it using radians. And to get an angular speed, we need to measure it per unit time. So it would be per unit time. And so per unit time. How many degrees is it spinning per unit time? How many radians is it spinning per unit time? How many revolutions is it doing per unit time? These are all ways of measuring angular speed. And then a bike works by transferring via a chain the angular speed at which it's being pedaled back to a smaller sprocket that's connected to a larger tire. So as you spin the front sprocket, the angular speed gets transferred into a linear speed in the chain, a linear velocity, and then that linear velocity gets transferred into an angular velocity, spinning the small sprocket, which also then spins the larger wheel. So we get angular speed transferring to a linear speed, transferring back to an angular speed, which then causes the bike to move forward in a linear speed. And so a classic question to ask is, hey, given a certain speed at which you're pedaling, how fast is the bike moving? But before we tackle something more complex like that, let's look at the big idea, the big concept. So the big concept is that if you have a circle that is spinning, revolutions per minute, degrees per minute, radians per minute, if you're a bug on this object as it's spinning, for every revolution this object spins, if it does one revolution, you have traveled the circumference of the circle that's spinning. You've gone around that object one time and you've wound up back where you started. So the circumference of a circle is given by 2 times pi times the radius of that circle. So in a single revolution, you traveled this many linear distance units, whether it's inches, feet, centimeters, millimeters, whatever your linear distance measurement is. So we can convert between angular and linear speed by understanding that we travel the circumference of the circle every time we do one revolution. And this gives us a relationship between linear and angular speed. And this relationship can be reciprocated. We can write it either way. We can say, hey, I'm going to do 2 pi r centimeters per revolution, or just as easily say, hey, I'm going to do 1 revolution for every 2 pi radius centimeters. So we can have the angular measure in the numerator or the denominator, and we have a valid relationship either way. And we could just as easily do 2 pi r units per, if we're doing 1 revolution, that's the same as if we're doing 360 degrees. And so we could say every 360 degrees we do 2 pi r linear units, or the circumference of the circle. And we could do it in radians. We could say, hey, 2 pi r linear units happen every time you do 2 pi radians, and we can reciprocate this relationship just as easily as the others. We get 2 pi r linear units. The nice thing here with radians, what do you notice? You notice that this would reduce to 1 over 1. We get 1 radian per radius, 1 radian per radius, which is really a nice relationship for every. 1 radian of motion corresponds to 1 linear unit of movement. So let's apply this concept in an application problem. So here we have a kid's merry-go-round with a radius of 56 inches. So kid's merry-go-round, radius 56 inches. And we're told that it's spun at 3/4. So 3/4. 3/4 what? Revolutions per second. So we're given an angular speed. And I'm going to put the units onto this 3/4. 3/4 what? 3 revolutions per is the fraction bar. Per what? Per second. So 3/4 revolution per second is the same as 3 revolutions per 4 seconds. And the first problem says find the angular velocity in radians per second. So we're given an angular velocity in revolutions per second, and we're just being asked to convert it over to radians. And what we want to understand is that each time we go around 1 revolution, that's the same as having gone 2 pi radians. And if we want the angular speed in radians per second, that tells us we want time in the denominator and radians in the numerator. So I'm going to walk over here and I'm going to put 2 pi radians in the numerator position, which is where it needs to be in the answer. And I'm going to use this relationship between radians and revolutions. It's 2 pi radians per 1 revolution. Revolutions divided by revolutions is 1. So revolutions have canceled out using dimensional or unit analysis, leaving us with a measure that's in radians per second. So we have 3 times 2 pi over 4 times 1. It looks like 2 will go into 4 twice, so we get 3 times pi is 3 pi. Radians per 2 times 1 is 2 seconds. So we can write it like this, 3 pi radians per 2 seconds, or we can just say 3 pi over 2, and then we could say radians per second. Part B says, what is the linear velocity of the kids who are riding on the rim or the outer shell of this merry-go-round? What is their linear velocity? What's their linear speed? So we know that we have been given, right here, we have been given an angular speed. I could just as easily use 3 pi radians per second as my angular speed just as well. So maybe we'll do this 2 different ways. So I could start with my angular speed of 3 revolutions per 2 seconds. And we want speed in miles per hour. Maybe it will be easier just to do it one way. We're going to string together a sequence of relationships that gives us the answer that we want using dimensional analysis. So the final answer needs to be in miles per hour. So what we see is we need miles in the numerator and we need hours in the denominator. So we're going to use dimensional analysis like we were doing up here, but in a little bit more complicated context. So 3 revolutions per second, but this wheel, this merry-go-round, has a circumference that's equal to 2 times pi times its radius, and its radius is 56 inches. So this equals 2 times 56 is 112 pi inches. This is the radius of the merry-go-round, so it has to go this far each revolution. So I'm going to use that relationship. I'm going to say, hey, every time we go around the merry-go-round one time, we have gone 112 pi inches. That's going to happen every 1 revolution. We go around one time, 1 circumference per 1 revolution. So the revolutions will cancel. Revolutions divided by revolutions is 1. I see that some simplifying can already start happening. 2 goes into 112. What's that going to be? 56 times. So right now I have a speed in inches per second, but I'm supposed to be in miles per hour. But I know that there is 1 foot per 12 inches, and inches divided by inches is 1. So I'm left with feet per second right now as a linear speed. It looks like some canceling can happen here. 3 goes into 12 4 times, and 4 will go into 4 once. 4 goes into 56 14 times. So I'm just going to cancel things as I go to keep the numbers as small as I can. So right now I have a linear speed in feet per second, but I need miles, so I need to convert from a foot world to a mile world. And so I know that there is 1 mile for every 5,280 feet. And now I get feet divided by feet is 1. Now I have a speed in miles per second. And it looks like some canceling can happen. I know 2 will go into 14 7 times, and 2 is going to go in here a whole bunch of times. 2 will go into 5 twice, 6, 4, 0. And will 7 go into that? That is a good question. 21, 21, 50. I don't think so. We'll come back to that. Miles per second, and then times. Now I need to get seconds converted into hours. So I know that there are 60 seconds per 1 minute. So seconds divided by seconds cancel, leaves me with miles per minute. I see that this 10 will go into each of those, and 2 will go in there 3 times. So we get 1. 2 goes into here, 132. And the 3 will go in here evenly as well, it looks like. So 3 will go into this. 3 goes into there, 12. We get 4 times 3 is 12. 44 times. And we're in miles per minute. We need to make one more conversion. We know that there are 60 minutes per 1 hour. So minutes divided by minutes is 1, and now we're left with miles per hour, and we can do a little bit more canceling here. I know it's going to go, 2 will go in there 30 times, and we'll go in here, what? Oh, we could have done 4. 4 will go into 60 15 times, and into 44 11 times. I think that's all the canceling that I see. So we have 1 times 7 times pi. There's that pi hiding right there. 1 times 7 times pi times 1 times 15. So 7 times 15 is 105 pi. And on the bottom we're multiplying a whole bunch of 1s until we get to this 11. So we get 105 pi over 11 miles per hour. And it might be interesting to get an approximation for that using the calculator. It's 105 times pi, and we're dividing by 11, which is giving us 30 miles per hour, which I don't like. That seems high. And because it seems high, if this were a homework problem or a test, I would walk back through this and double check my canceling just to make sure that it was correct. Again, 30 miles per hour seems fast. Seems like it would make you sick.